Thanks. I'll begin. Dear Heavenly Father, we thank you for this morning. Again, Lord, I thank you for these students. Just pray that you just continue to encourage them to work on this class and their other classes, Lord, for your glory. And we thank you for your truth, which we can study and enjoy, Lord. In your name I pray. Amen. Okay, so I'm going to start with a few theorems. And then once my brain is tired, I'll flip over to L'Hopital's rule, which is easier. So here we go. So I'm going to start with the proof of the bounded monotonic sequence theorem. This stuff over here is just a collection of things that, things you should know, really. But here's the theorem. I call it the bounded monotonic sequence theorem. It's 11.3, 11.36. States the following: an increasing sequence an, which is bounded above, converges to the least upper bound of the range of the sequence. Now, if it converges, what can we say about it from last time? Well, not from last time, but before the last time. It's what? Yeah, last Friday. If a sequence is bounded, or excuse me, rather, if a sequence is convergent, it's what? It's bounded, right? So this, we assume it's bounded above, but by the way, once you know it converges, it's also bounded below, all right? And likewise, in number 2, you assume you have a decreasing sequence which is bounded below. You're given that it converges to the greatest lower bound of the range. That's what the theorem says. So if you think back to last class, it then follows, of course, that it's also bounded, in case 2, above. So a simple way of remembering this theorem, which kind of lumps together that other theorem into it at once, is simply that if you have a bounded monotonic sequence, it converges, or the so-called bounded monotonic sequence theorem. Okay. So I'll prove one here, step by step. Any questions before I start? Oh, first of all, your homework will be due Thursday, all right? So you should be able to ask questions about it tomorrow if you want, all right? The test is pushed back 1 week. It was supposed to be Tuesday. It'll have to be the Tuesday after. So not March, what was it originally, March 1st. Now, I guess in principle I could keep it, if you guys want me to, I could keep it March 1st. I mean, no? Nobody ever takes me up on that. It's the weirdest thing. So, March, will you know the stuff by then? Well, that's up to you. I mean, I can explain it to you. I can't understand it for you. Let's see here. So March 8th. That's not my saying. I got a T-shirt with on it, and I like it. But, I can't take credit for that. March 8th will be test 2. Okay. Now, it seems very likely that we will finish lecturing and covering the material which is on test 2 before then, and so there probably will be a couple days where we cover material which is not on the test, but will be on test 3. Otherwise, we'll never get back on track, obviously, right? So, anyway, that's not today. I will let you know when we're past the material which is on test 2. It's not that complicated, really. You can look at the course planner and you can see exactly where that is, all right? Okay, so here we go. Suppose you have a bounded sequence, a sub n, which is bounded above and is increasing. Increasing means that a sub n is less than or equal to a sub n plus 1. Okay, so Allison-Hilley calls it non-decreasing. Fine. Let L be the least upper bound of this, which we know exists by the least upper bound axiom, right? Then that means, of course, it's an upper bound. A sub n is less than or equal to L for all n. Great. Let epsilon be greater than 0. Okay. My goal, of course, right, if I want to prove this limit exists, I want to do what? I want to pick epsilon greater than 0. I need to give you guys some positive integer so that if you're beyond that, the difference of a sub n minus L is less than epsilon. If I can do that, if I can show that the distance between a sub n and L is less than epsilon beyond some point in the sequence, then I'm golden. I've proved what I need to prove. So I start with an epsilon greater than 0. I have to pick an arbitrary epsilon greater than 0. But we have this theorem 11.1.2, which we proved in here pretty carefully, that you can find another point in the set. In this case, a sub k is in the range, the non-empty subset of real numbers we're thinking about. We can find a sub k such that L minus epsilon is below a sub k, and a sub k is between the least upper bound, right? Remember we proved that if this weren't the case, then L minus epsilon would be itself an upper bound, which was smaller than the least upper bound. Oops. Okay, so we proved that that was theorem 11.1.2, which we proved with contradiction. But we already know that. We don't have to prove it again. So there exists some a sub k between L minus epsilon and L. All right. But we have an increasing sequence, right? So that means that a sub k is less than or equal to a sub n. Now notice this k is fixed, all right? It's given to us by the theorem 11.1.2. So for all n greater than or equal to k, we have a sub k is less than or equal to a sub n. At that point, you're pretty much done. You just have to collect your thoughts, and you'll see you already have what you need. So if ignore this for now. For n greater than or equal to k, all right, for such n as that, we have L minus epsilon is less than a sub k. But what else do we have? Well, a sub k is less than or equal to a sub n. Because the sequence is what? It's increasing, right? So if I increase the index, I increase the value. This is by definition of increasing in the fact that n is greater than or equal to k. But hey, L is an upper bound on the sequence, right? So a sub n is less than or equal to L. But then certainly you can add a positive quantity, right? So what I have then is I have L minus epsilon is below a sub n, and L plus epsilon is above a sub n. If I subtract L from this on both sides, I get minus epsilon is less than a sub n minus L is less than epsilon. But that is exactly what I need in order to prove that the absolute value of a sub n minus L is less than epsilon. So I don't know if you guys knew this or not, but to go back and forth between inequalities and the inequality for an absolute value, this is the way you do it. If I can prove like minus epsilon is less than a is less than epsilon, then that is what it takes to prove that the absolute value of a is less than epsilon, right? So there you have it. A sub n goes to L. The theorem's proved. Any questions? Really just a simple combination of the things we've done so far. Assuming you understand the definitions, which of course is assuming a lot. I mean, you guys aren't used to learning new definitions in math and working with them. But I suppose if you already knew the material in this class, there would hardly be a point in taking it, right? So that pain you're feeling is the learning process. It's good. If you're not feeling that, you should drop the course and just try to like test out of it or something, right? I'm really making an argument that you should drop out of every psychology or history course you've ever taken. Oh, I'm sorry, history. I mean, well, I don't know. There's something called the liberal arts education. Some people believe in it. I don't know, whatever. I'm a specialist. It doesn't make sense to me, but whatever. So a simple application of this theorem that's really nice is we've already kind of seen this application, but I just kind of cheated, and I used your intuition. We looked at something like, 0.b1, b2, bn. That's the nth term in the sequence, right? So if b is defined by some sort of unending decimal expansion like this, whatever that means, and if you really think carefully, maybe this isn't really defined yet. So this example is a little bit out of place. But it's useful, though. We will define this kind of thing carefully. That's the next chapter, actually. This is an infinite series. That said, setting aside that cheat, if this does go to b, then b is certainly an upper bound for this sequence, right? And so you have an increasing sequence which is bounded above. Consequently, it converges. And it must converge to that b. In other words, this bounded monotonic sequence theorem, it justifies, it affirms our intuition the other day that square root of 2 sequence really does converge to the square root of 2. Because the digits in the square root of 2 will give you an example of an increasing sequence which is bounded above. So the connection between rationals and irrationals is very much tied in this least upper bound axiom. Yeah, hot. Okay, next. Limit laws. You know them, you love them, you miss them, right? Not really. Not really. I know you guys want to go outside in the hallway and do like a little dance when we get past limits in Calc 1. I know the happiness, it's palpable. There's definitely a non-trivial percentage of calculus students who are literally annoyed that we covered the definition of the limit in Calc 1. You can't do anything with it. What does it matter, right? I mean, well, I don't know. Logic, foundations, stuff like that. You guys don't care about that. Some of you don't care about that. Anyway, so we also have limit laws for sequences, and here they are. If we have a sub n going to L and b sub m going to m, in other words, the limits of those sequences exist in our L and m respective. And if alpha is a real number, then the a sub n plus b sub n goes to L plus m, alpha times a sub n goes to alpha L, a sub n times b sub n goes to LM, and so forth. All right. So these are your limit laws. Let me just point out, once you know these, I'll do the proof here in just a second, but for example, once you know them, you can easily show that if you have the limit as n goes to infinity of something like, I don't know, 3 n to the 6th plus 4n minus 7 divided by n plus n to the 6th minus 2, right? If you have this and you know something more basic, like suppose you've also proved that the limit as n goes to infinity of 1 over n is equal to 0, right? If you have that, then you can easily extract from that the limit of 1 over n to the, say, p power is also equal to 0, where p is a positive integer, right? You can be greedier than that, but certainly it's true for p in the natural numbers. I mean, oh heck, you could let p be greater than 0, it would still be true, but this, if you know that, then you can get to this by just using like the product theorem, right? Like 1 over n squared is 1 over n times 1 over n. So if I know 1 over n goes to 0, then surely 1 over n times 1 over n goes to 0. And you can kind of bootstrap your way on up from there using 3. Or to be more careful, you could use an inductive argument. Anyway, we'll find lazier ways today. But the point here is just, once you have these limit laws, you can calculate limits like this pretty easily, right? Like this, for example, what you do is you just pick the largest power, okay, which is in this case what? 6. And so I get like 3 plus 4 divided by n to the 5th minus 7 over n sixth, n to the 6th, over 1 over n to the 5th plus 1 minus 2 over n to the 6th. All the 1 over n stuff goes to 0, all right? And using the limit laws, essentially, this is going to be equal to 3. Well, I'll write it this way. 3 plus 0 minus 0 over 0 plus 1 minus 0, also known as 3. Okay, so once we know the limit laws, then we can calculate limits of rational sequences with this idea. No big deal. Oh, fine, I'll do this again. I was trying to be lazier. Okay, so let's prove. I'm going to show you the proof of one. Proof of one. So assume that a sub n goes to L and b sub n goes to M, as in the theorem, and I'll let epsilon be greater than 0. Note, since a sub n goes to L, there exists some big N sub a in the natural numbers such that whenever n is greater than or equal to n sub a, that implies that the absolute value of a sub n minus L is less than epsilon over 2. Likewise, since b sub n goes to M, there exists n sub b in the natural numbers such that n greater than or equal to n sub b implies that the absolute value of b sub n minus M is less than epsilon over 2. I'll take a breather here. Why is this true? I mean, why can I find an n sub a and an n sub b to make it so? What does it mean for the limit of a sub n go to L? Remember what it means? It means for each positive number, I can find some positive integer so that if I go beyond that positive integer, within that positive real number units from the sequence and the limit point. In other words, I can make the difference between a sub n and L as small as I like by going far enough out in the sequence, and likewise for b sub n minus M. In particular, I can make it within epsilon over 2 and epsilon over 2. Now you could ask, why on earth are you doing that? Okay, well that will become clear shortly, right? I haven't explained yet. Right. Now my next move is I'm going to let n equal to the max of n sub a and n sub b, right? And notice that if n is greater than or equal to n, then surely n is greater than or equal to n sub a, and n is greater than or equal to n sub b. So what that means then is for such n, very greedy, I don't get one of the fun facts, I get both of the fun facts, which I will shortly underline in red. I get the fact about a sub n and I get the fact about b sub n, because I control both of them at once by choosing the max, like so. All right, so then consider the absolute value of a sub n plus b sub n minus parentheses L plus M. Notice that if I can show that that's less than epsilon, I'm done. Because I will have then shown that for every epsilon greater than 0, there exists a positive integer such that when n is beyond that positive integer, the distance between the sequence and the alleged limiting value is less than epsilon. Epsilon being arbitrary, I've done my job. So here, first of all, an algebra step, a sub n minus L plus b sub n minus M. My next move is the triangle inequality, which I've written over here because this is my list of things that you should know. Okay, we'll come to those at various points in the lecture today. So here we go. This is less than or equal to the absolute value of a sub n minus L plus the absolute value of b sub n minus M by the triangle inequality. Going from here to here, I'm using the triangle inequality. Then what? Yeah, it's less than epsilon over 2 plus epsilon over 2, which is, in fact, epsilon, yeah. Hence, thus, a sub n plus b sub n goes to L plus m. Oh, I tend to write this to say I'm done with the proof. Your textbook likes to write these little boxes. Other people write QED. I just can't do it. Exclamation point. But then when I'm proving something about a factorial, it will be very confusing. So I can't do it. Thank you, though. Now, of course, what we've just proved is this really, if you write it in terms of limit notation, it looks like this, right? But there's some advantage of the way the book writes the theorem because it makes clear what you're assuming. You're assuming that L and M exist to start with. Given the existence of these limits, we get the existence of the sum limit, not the other way around. Okay. Like, for example, it is true that the limit as n goes to infinity of n minus n is equal to 0. But it is not true that this is equal to infinity minus infinity, as you might be tempted to say, because the limit as n goes to infinity is infinity. Infinity minus infinity is not 0, it's an indeterminate form. And what I just wrote is nonsense, because you can't go the other way around. The existence of the sum does not imply the separate existence of the things which are being summed. It's just not the case. But anyway, I guess we're not obligated to tell you all the various ways that the theorem breaks down when you change it a little, so we can go on. Okay, so 2. How would you prove 2? And we'll just say, okay, so if alpha equals to 0, then a sub n, then alpha times a sub n is equal to 0, right? And so the alpha a sub n minus alpha times what? L is equal to 0, which is automatically less than epsilon, so therefore alpha a sub n goes to alpha L. Okay, great, we're done. If alpha is not equal to 0, though, maybe it's interesting. Suppose a sub n goes to L. Let epsilon be greater than 0. Then what? Since a sub n goes to L, we can select n sub naught in the natural numbers such that n greater than or equal to n sub naught implies the absolute value of a sub n minus L is less than you fill in the blank. Consider the absolute value of alpha times an minus alpha L is equal to, well, alpha times a sub n minus L, which, by the way, is equal to the absolute value of alpha times the absolute value of a sub n minus L, less than something, and then I want that to be equal to epsilon. All right. So I'm making a, here, let me put it in red. I'm trying to choose our own adventure here, so we can fill in those blanks. Oh, the audio working? Every so often. At this point, it would be sad to find out otherwise. Okay. Again, since a sub n goes to L, you can make this as small as you like. Right? How small do you want to make it? 0? You can't make it 0. You can make it not 0. 0 is you're too greedy. Any positive integer, you can make it. What's that? fine. We have alpha here. I want to put something here that gives me alpha, epsilon. So what should we do? How about this? Epsilon divided by what? 2. Why? 2. Absolute value of alpha over 2 wouldn't be 1. And alpha could be negative. Alpha won't work either. Absolute value of alpha, yes. So we put epsilon over absolute value. You guys are killing me. Epsilon over absolute value of alpha will do it. That is a positive quantity, right? If alpha was minus 3, I couldn't choose epsilon over minus 3 to be a small positive number, could I? No, I could not. And it's just as well because I want to cancel absolute value alpha with absolute value alpha here anyway to give me epsilon. Oh, and we're done. Thus, alpha times an converges to alpha times L. Because I have shown that for epsilon greater than 0, there exists an integer, in this case n sub naught. I guess I should emphasize here. Actually, this proof isn't quite right yet. I really should write here again for n greater than or equal to n naught. I mean, I was assuming that when I wrote those steps, but to be clear, we're assuming n is greater than n naught, where n naught is the specific positive integer, which makes absolute value a sub n minus L less than epsilon over absolute value of alpha. Okay. Now, to prove 3, 3 is hard. Okay. 3 is not like the others. 3 is difficult. It's in an appendix to this section. We're a little bit short on time, so I probably won't do that this semester. 4 and 5 aren't too bad once you know 3, I think. For example, if we know 3 and 4, it's easy to get 5. Here's the argument. So if I know 3 and 4 are true, then if I look at a sub n over b sub n, right, that's a sub n times 1 over b sub n. Using 4, this converges to 1 over m, but that's L over m. Bam. Done. And I'm going to give you a proof of 4 using a different theorem here in just a minute. Maybe we can even prove 3 with the other theorem. I'm not sure. I had to think about that some more. All right. I do hate to erase this, but I have to. All right. All right, so, oh man. Oh, silly. I thought I hadn't erased something, but I have. All right. I'll get over it, don't worry. If I can find a marker. A few other theorems that are true that I will state without proof, but the proof is very much like the ones I've already shown you. So, like, if I was asked to prove one of these things, you probably could do it once you understand the other ones. Now, if you don't understand what I've done already today, the chance that you can prove this, well, there's still a chance, actually. There's still a chance. Let's see here. So the following are equivalent. You can either talk about a sub n, if a sub n converges to L, okay, that is equivalent. You can trade it for a sub n minus L converging to 0. And that you can trade for the absolute value of a sub n minus L converging to 0. So these are 3 different ways to look at the same thing. That's theorem 11.3.8. Theorem 11.3.9, we have if a sub n is less than or equal to b sub n is less than or equal to c sub n, and if you have a sub n goes to L, and c sub n goes to L, then what's up? Yeah, B sub n also goes to L. Now, I'm missing a little bit of fine print here, which is kind of important. What's the condition here? This has to be true for n greater than or equal to n naught. Some n naught. I mean, it doesn't have to be true for everything in all three of these sequences, but if you go far enough out, it has to be the case that you have this inequality. Okay. If it's violated, say, up to like the 20th term in the sequence, we don't care, as long as the inequality holds for 22 forever. What is this called? I usually call this thing the Sandwich Theorem, or some people call it the Squeeze Theorem, right? Squeeze Theorem. There is a corollary to this, which states the following. If the absolute value of a sub n is less than or equal to c sub n for n greater than or equal to n naught, all right? And if Cn goes to 0, then An goes to 0. Probably be good for me to prove some of this stuff. I will not prove the squeeze theorem. The squeeze theorem is of similar technical difficulty to the product theorem over here. It's quite involved. I have a proof in my Calculus 1 notes that you can look at if you want. And it's probably in the appendix of the book as well. So let's see here. This corollary is pretty simple. Like the proof of the corollary, here's how it goes. Right. If you know that the absolute value of a sub n is less than or equal to c sub n, right? What does that mean? Go back to my fundamental comment. This is how we go between absolute value inequalities and inequalities. To unwrap an absolute value inequality, you go plus or minus the thing, right? So this is interchangeable with minus Cn less than or equal to a sub n less than or equal to Cn. Okay, so, but Cn goes to 0 implies that minus Cn also goes to 0. Therefore, a sub n goes to 0 by squeeze. I'm using 2 without the equals to minus 1 and L equal to 0. I mean, the proof of 11.38 isn't really that complicated. I mean, like, check this out. If you have a sub n minus L less than epsilon, what does that mean? Well, that is true, but let me state something even more boring than that. No offense. I mean, how about this? If I just do this. So like, if n is a positive integer that makes this less than epsilon, right? Then n is also a positive integer which makes this less than epsilon. But that is exactly what I need to prove that the sequence, if you look at this collectively, is like a b sub n, right? So b sub n goes to 0 from this inequality. And by the way, that's the same as this. So the equivalence of those inequalities gives you the equivalence of these sequential limits. If n makes any one of those less than epsilon, it makes the other two. less than epsilon as well. That's the proof which is omitted. Again, I'm not going to try to prove the squeeze theorem. Ugh, scary. No, definitely not. But what I will do is show you how to use corollary 3-point. 3-point, this doesn't look like much, but when you understand what it does for you, it's very powerful. So for example, if I have something like cosine of n cubed plus 37n, all right, divided by n, and I want to look at, what happens as n goes to infinity. Well, cosine of n cubed plus 37n, that's kind of nasty, right? But the thing is, if you look at the absolute value of this, right, this is less than or equal to, well, that's the thing about cosine. Cosine is bounded by 1, right, above plus or minus 1. And so, yeah, so it's just 1 over n, right? But 1 over n goes to 0, right? So therefore, cosine of this ugly n cubed plus 37n divided by n goes to 0. So corollary, very useful for limits which happen to be 0. Now your textbook says some various things about the exponential function through sections 11.2, 11.3, 11.4. I'm deliberately avoiding those because I want to come back and talk about the exponential function from a slightly different perspective, in particular L'Hopital's rule. So I'm deliberately not talking about it as the book talks about the exponential because I think my way is easier. And it may not be quite as logical as the book, but I think you'll find it is worthwhile. We'll see. All right, next theorem. Any questions? Hopefully not about what I'm erasing. Okay. This is theorem 11.3.12. This one's pretty. I mean, this is a very, very useful theorem. This theorem essentially will enable us to do wholesale theft from Calculus 1, which will be very nice. So suppose Cn goes to C, all right? And if the range of Cn is a subset of the domain of a function, f, and if the limit as x goes to c of f of x is equal to f of c, right, then f of Cn goes to f of c. Can you put this in words for me? What is this formula I wrote about the function in x going to c? What's that mean? F is what at x equals to c? This is what it means for f to be continuous at x equals to c, right? The continuity of the function at c. This formula, all I'm really saying here, all this really means is that f of Cn makes sense. Right? Let me just put it in common terms. Saying that you can evaluate the function on the sequence. Okay? That's all it's saying. And the conclusion, the punchline here, it's fun to rewrite this in terms of limit notation. What this is saying is that the limit as n goes to infinity of f of Cn is equal to f of the limit as n goes to infinity of Cn. in the case that the limit exists. In practice, this is usually also true if the function's continuous to infinity. I mean, you can state this has an extension past the point where the limit exists in terms of functions being unbounded and having a sequence which is also going to infinity or something. I mean, there's a little bit more. You can state a greedier theorem, which includes the divergent cases, but we'll stick to what's stated. So what this is saying is that if a function's continuous, you can pass a sequential limit inside it. Remember, we had a similar theorem for limits as like x goes to 3 or whatever. For a continuous function, you can bring a limit inside the argument of the function. Remember that? One of our basic limit laws. Okay, so how do you prove this? So proof. So suppose f continuous at x equals to c and Cn goes to c. Let epsilon be greater than 0, and by continuity, of f, choose delta greater than 0 such that the absolute value of x minus c less than delta implies that the absolute value of f of x minus f of c is less than epsilon. That is the epsilon delta definition of the limit from last semester. So there it is. Next, since Cn goes to c, right, choose n sub naught, an element of the natural numbers, such that n greater than or equal to n sub naught implies that the absolute value of Cn minus c is less than what? You fill in the blank. Thus, the absolute value of f of Cn minus f of c, well, I'll put it over here. Thus, the absolute value of f of Cn minus f of c is less than epsilon, and we're done. So I'll just say here we're thinking basically x is equal to Cn. See up here? I have Cn converges to C, right? I have complete control over how close Cn and C are as you go far enough out in the sequence, right? How close do I want to make these so that I can use what's in the green in the case x is equal to Cn? Can somebody tell me? Nope. Not epsilon. Yeah, what if I put delta there? So if we put delta here, right? If I put delta here, then look at it. X equals to Cn, right? Satisfies this criteria, and hence this inequality is met. But that's exactly the inequality that I need. Therefore, f of Cn goes to f of c, which is what we set out to prove. Nothing really as sophisticated as this one, or the one I've erased, about the sum, right? Because, I mean, really I'm just stringing together the definition of continuity from Calc 1 and our current definition of sequential limit. They just nest together to give you this theorem, basically. But that's not to say that this theorem is trivial. This theorem is far from trivial. It is stupidly useful. And the only way that it becomes stupidly useful for you is if you remember those things that we already know from Calculus 1. So just a comment. You know, the library, let's say, I don't know what you want to call it, lexicon, whatever, of functions from Math 131 are continuous on the interior of their domains. So what functions do we know about? How about x to the n, 1 over x, square root of x, pick your favorite algebraic function, right? E to the x, cosh x, sine x, cosine x, tangent x, cosecant x, cotangent x, hyperbolic cos x, tanh x, dot, 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 dot. All of the functions we've touched on this semester. Pretty sure. Did I ever tell you about this one? The only thing I can think of that we come across that's not fitting the bill is like this one. How about this? X over the absolute value of x. What's this? It's either x over minus x or it's x over x, right? Oh man, even this fits the bill, right? Because this guy looks like this. It, in fact, 0 is not in the domain. It's still continuous on the interior of its domain. 0 is not in its domain. It can't be discontinuous at a point where it's not in its domain. So some of you guys have been, well, I don't know. It's a question of pedagogy in some sense. But here's the y equals f of x equals to 1 over x, right? This function is continuous on its domain. Some of you have been taught it has a discontinuity at 0. I know what the instructor meant by that, but I don't know how to judge discontinuity at a point which isn't in its domain. 0 is not in the domain of the function. I can't say if it's continuous or not there. I can't check the limit as x goes to 0 of f of x. It doesn't even exist. Certainly it is the case that this function is continuous at x not equal to 0. Okay, so anyway, enough about this stupid subtle point. My point to you is really just this. Almost any expression you can think of, if you can plug something into it, right, and it makes sense, the expression is continuous at that point. All right? That's what I want you to take away from this discussion. Now, so, with that, everywhere continuous. Let epsilon be greater than 0. Choose delta equals to epsilon. Then the absolute value of x minus absolute value of a. If 0 is less than x minus a, is less than delta, then this. Oh man, you're distracting me. Hold on a second. I mean, you can prove. I don't have to prove that. The absolute value of x is everywhere continuous, right?
Okay. It's not differential, but it's still.
Yeah.
What kind of function is there that isn't continuous on its domain?
Exactly. Exactly. So, an example, something like this, 2n minus 1 over n, all right? So that's equal to 2 minus 1 over n. This, of course, goes to 2, right? So here, this is playing the role of the Cn, okay? All right. And then you can look at various functions like f of x equal to the square root of x, or f of x equal ln of x, or f of x equals to 1 over x. The last of those makes sense as long as x is not equal to 0. The first two require that x be, well, square root of 0 is fine. Natural log of 0, not so good. Certainly if x is positive, we're good to go. But if you look at this sequence, right, the smallest it is what? One, right? N equals to 1, 2 minus 1 is 1. And then it's like 3 halves. And it just gets, it goes to 2. So clearly this sequence is positive. So these are fine. In other words, f of Cn makes sense. Okay? So consequently, the square root of 2n minus 1 over n goes to the square root of 2. The natural log of 2n minus 1 over n goes to the natural log of 2. 1 over 2n minus 1 over n, also known as n over 2n minus 1, goes to 1/2. All by Theorem 11.3.12. Is very nice, yes? I don't know about you, but personally, the thought of trying to find an n for a given epsilon greater than 0 that makes the difference between this and the root 2 be less than 0 frightens me. That doesn't seem like a very cheery proposition. But with this theorem, I can avoid that difficulty of directly arguing from the definition, right? It's very nice, very nice. By the way, now that we have this, right, we could do other things like, I don't know, how about this? If the limit, let's see here. How can I say this? If the limit as x goes to how to say this, m of f of x is equal to f of m, and the limit as x goes to L of g of x is equal to g of L, right? Oh, that's not what I want. Fine. I'll do the one I know how to do. F of x equals to 1 over x, right? My point is we can prove 4. We can prove 4 over here. So let's see here. Let f of x be 1 over x, right? And b sub n not equal to 0, right? Then f of bn is, defined, right? And if b sub n goes to m, which is not equal to 0, right? Then f of bn goes to what? Goes to f of m. In other words, what? 1 over bn goes to 1 over m. So I can easily use theorem 11.3.12 to prove 4 via the reciprocal function's continuity. Very nice. I think there's got to be a way. There's got to be a way to get 3. I just how to do that. I don't know. I got a mental block on that one at the moment. Any questions? Go for it. Yep.
Pretty much you're just trying to get epsilon by itself, correct?
Yeah, that's the end game. We want to show that the absolute value of the sequence minus the limit value is less than epsilon. And I have to somehow do that with the data which I'm given. And I haven't shown you guys how to construct those theorems. I've showed you an argument which is true. I did not show you how to arrive at that argument. So, I mean, we kind of see it for 2, right? If you kind of followed 1 along a little bit, maybe you had a chance at following 2 and maybe even finding the choice of what to make the, absolute value of an minus L less than yourself, epsilon over absolute value of L. But the actual process of constructing these proofs, what I do at least, is I look at what I want, which is the sequence minus the limit less than epsilon, and then I try to work it into other things and then see what I could choose at the start to make that happen. But none of those things are the proof. Those are just scratch work. Some of you maybe remember this from Math 131, the scratch work going into the epsilon deltas. It's the same song and dance. It's just there we're choosing a delta which is small to make x close enough to the limit point, right? Things have flipped over here. Now we're finding an n, so that when n is beyond that, when n is really big, we get close. So these are kind of like dual thoughts, but the construction of the proofs is much the same. So I think I've covered pretty much everything in 11.3 at this point, guys. Believe it or not, that's pretty much it. The other comment I should make is about the stability of the limit, and I was already kind of touching on that with these. Here, let me do another little theorem that's useful. Theorem. If Cn, well, let's say an is equal to C for n greater than or equal to n naught, then an goes to C. So I'm not saying that this is a constant sequence, all right? I'm saying that this is an eventually constant sequence. It could do all kinds of crazy stuff for the first 300. I don't care. If it's always 3 past that point, the limit's 3. Because the limit of a sequence only cares about the tail of the sequence, basically. So here's the proof. You let epsilon be greater than 0. Choose n equal to n naught, really, all right? And suppose n is greater than or equal to n naught, then the absolute value of a sub n minus c is what? Well, I'm assuming a sub n is as in this theorem here, right? I should say assuming a sub n is equal to c for n greater than or equal to n naught. This is equal to ac minus c, which is 0, which of course is less than epsilon, so we're done.